Hello student, I am Latif sir. Today I will discuss about IC class 12 chemistry. The topic is the solid state chemistry. In the last video I have already discussed about the defects in crystal, different types of defects in crystal. Uh, that is stoichiometric defects and stoichiometric defect and impurity defects. I have already discussed. Today I will discuss about non-stoichiometric defects. First you have to know what is non-stoichiometric crystal. Non-stoichiometric crystals are those which do not obey the law of constant proportion. Non-stoichiometric crystals are those which do not obey the law of constant proportions. The number of positive and negative ions present in such compound are different from those expected from their ideal chemical formula. The number of positive and negative ions present in such compounds are different from those expected from their ideal chemical formula. However, the crystal as a whole is electrically neutral. That is in neutral condition. Okay, these are non-stoichiometric defect. And what is non-stoichiometric defect? Non-stoichiometric defects in non-stoichiometric crystals. There are two types of non-stoichiometric defects are as follows: metal excess defects, and second one is metal deficiency defect. Metal excess defect and metal deficiency defect. First, metal excess defect. A metal excess defect may arise due to first, vacancy at anionic sites, or second, extra metal ion in the interstices. Okay, metal excess defect may arise due to vacancy at the anionic site or extra metal ions in the interstices. So let's see the first one, anionic vacancy. Anionic vacancy is when NaCl is heated. First, I am showing you a drawing. In this is a crystal lattice of NaCl, sodium chloride. You can see sodium chloride. Here, when sodium chloride is heated, then you will see that sodium chloride becomes yellow. This is because after during heating, one chloride ion or many chloride ion may be leave that crystal lattice, losing one electron. So here I have shown the electron. One electron is present. E minus. E minus is electron. Electron occupies the vacant site formed by leaving one Cl minus ion, chloride ion from the initial lattice. And here the site in which electron present, E minus present, is known as F center. Okay. Due to the presence of this electron, or due to presence of F center, the sodium chloride lattice become yellow. So what is the actual phenomenon occurs during the heating of NaCl? So let's see. Anionic vacancy. When sodium chloride is heated in the presence of sodium vapor, sodium atoms deposit on the crystal surface and occupy the cationic lattice points. Chloride minus Cl minus ion occupy Cl minus ion diffuse to the surface, leaving vacant anionic site. So Cl minus ion diffuse to the surface, leaving vacant anionic site. The sodium atom at the surface combine with the chloride ion to form NaCl by losing electron, which occupy the vacant anionic site. The, so during heating, sodium chloride crystal in presence of sodium vapor. Okay, chloride minus ion leave one or more chloride ion leaves their position, forming anionic vacant site, and they lose electron. The chloride minus ion lose the electron lose by chloride minus ion will occupy the vacant site formed by the chloride leaving after leaving chloride minus ion, Cl minus ion. Thus, NaCl crystal has an excess metal atoms. That is, after leaving one Cl minus ion, there will be one Na plus ion extra. So, NaCl crystal has an excess of metal atom, and its formula becomes Na1 plus X Cl. Na1 plus X Cl. Here, one sodium atoms, sodium cation Na plus uh, becomes excess. The extra positive charge due to the excess of metal ion is balanced by the equal number of electrons. If if five chloride ion leaves their position or their sites, then there will be five anionic site, vacant anionic site, and there will be five extra Na plus ion. So here it is written that the extra positive charge, that is Na plus ions, charge of Na plus ion due to the excess of metal ion is balanced by the equal number of electrons. The equal number of electrons, the process cause a change in color of NaCl crystal, which become yellow, and the NaCl crystal become yellow. The color is due to the electron occupying anionic site. The color is due to the electrons occupying vacant and anionic site. Huh. These vacant anionic sites in which electrons occupy are called epicenter. Epicenter means the epicenter. Uh, the These vacant anionic site in which electron present are called epicenter after the German word Farben. Farben, Farben means color. So when light falls on the crystals, when light falls on the crystal, the epicenter electrons are excited to higher energy level by absorption of suitable radiation. When light falls on crystal, the epicenter electrons are excited to higher energy level by absorption of suitable radiation. Then we see the color of the radiation that is not absorbed. Thus, NaCl crystals turn yellow even when they are heated in presence of vapor of other alkali metals. So, this is the defects due to anionic vacancy. That is second one, extra metals ion. Here, one example given. The extra metal ions, if defects due to extra metal ions, it is explained by taking one example. When zinc oxide is heated, it turns yellow. Zinc oxide, like NaCl, when NaCl is heated in presence of sodium vapor, it becomes yellow due to presence of epicenter. Epicenter means the center in which electrons present, and electron balance the charge of cation, extra cation. Uh, Now, extra metals ions, when example, by it is explained by taking one example. When zinc oxide is heated, it turns yellow from white and turns white again on cooling. When zinc oxide heated, it becomes yellow. When it again cool, if you cool again, then it will be again white. On heating, what actually happens in this case? When zinc oxide on heating, zinc oxide dissociate reversibly to give oxygen. So the reaction is ZnO reversible arrow, Zn2 plus half O2, that is oxygen gas, plus 2 electron. So after heating, zinc oxide dissociate to form zinc 2 plus ion and oxygen gas and 2 electron. This leads to an excess of Zn zinc 2 plus ion in the crystal, and the excess Zn2 plus ion move interstices and the electrons to the neighboring interstices, and the color is due to the interstitial electrons, and the oxygen gas will leave the crystal surface. So this leads to an excess of zinc in the crystal, and the excess Zn2 plus ion move to the interstices, and the color is due to the interstitial electrons. Now metal deficiency defect, metal deficiency defect, second one, non-stoichiometric defense. Metal deficiency defect. Here it is also explained by taking example. Metal deficiency defect due to cationic vacancy. Metal deficiency defect due to cation vacancy. That is, some metal atoms, metals ion leaves their position from the crystal surface. So metal deficiency defect due to cation vacancy. It is due to the absence of metal ion from the lattice, and charge is balanced by ion having higher positive charge. It is due to the absence of a metal ion from its lattice sites, and charge is balanced by ion having higher positive charge. Transition metal exhibit this type of defect. Example, FeO, which is found in composition range from FeO, which is found in the composition range from Fe.93O to Fe.960. You can see Fe.930 to Fe.960. This is a composition of FeO. Hmm. In the crystal of FeO, some Fe2 plus cations are missing. In the crystal of FeO, some Fe2 plus cations are missing, and the loss of positive charge is made up by the presence of required number of Fe3 plus ion. In the crystal of FeO, some Fe2 plus cations are missing, and the loss of positive charge is made up by the presence of required number of Fe3 plus ion. And now classification of the basis of electrical conductivity. There are solids conductivity, first conductor, insulator, and semiconductor. You can see in the box conductors, insulator, and semiconductor. So let's say the conductivity of conductor is 10 to the 4 to 10 to the 7. That is very high conductivity of conductor. In for insulator, conductivity ranges for insulator conductivity is ranges 10 to the power minus 20 to 10 to the minus 20 to 10 to the power minus 10. That is very low. For insulator, the conductivity is very low. That is 10 to the minus 20 to 10 to the minus 10. For semiconductor, the conductivity is ranges 10 to the minus 6 to 10 to the power 4. That is moderate. Not very high, but moderate. For semiconductor, the conductivity is 10 to the minus 6 to 10 to the 4. That is moderate. Now, let's see the reason of conductivity. For conductor, the reason of conductivity is motion of electron. For conductor, the reason of conductivity is motion of electron. For insulator, the reason of conductivity is insulator, they do not permit electricity because their conductivity is very low. And for semiconductor, their conductivity is moderate, that is 10 to the minus 6 to 10 to the 4. And the conductivity of semiconductor is due to motion of interstitial electron or hole or both. Due to the conductive reason of conductivity of semiconductor is motion of elect interstitial electrons or holes or both. Now example of conductor are metals. All metals like aluminum, silver, copper, iron, these are conductor. Example of insulator: wood, rubber, bakelite, these are example of insulator. And example of semiconductor are silicon, germanium, etc. Now here this is a band theory for conductors, insulator, and semiconductor. You can see that figure given here. For conductor, the partially filled band, the band theory, conduction band bands are partially filled. For metals, their valence bond and conduction bond. Band is the upper box is conduction band, and lower box is which is marked by giving lines. Okay, so upper box is conduction band and lower is valence band. So in case of metals, you can see the overlapping bands between valence band and conduction band. For insulator, there are far gap, high gap between valence band and conduction band. You can see in case of insulator, there is a gap. The gap between conduction band and valence band is high, very high. That is for forbidden zone. Here it is written. For semiconductor, the gap between conduction band and valence band is small. That's why they can sometime can conduct uh, very small electricity. Okay, so this is band theory which explain the conductivity of different types of solid.